Hi there, and welcome to the lecture video for section 2.2 on the topic of properties of matrix operations. In this section, we are going to, of course, explore the properties of matrix operations, but we're going to see some pretty useful and fairly satisfying results that let us make a big connection between systems of equations and matrices. We're going to see why we spend so much time on matrices when what we're really studying in a linear algebra class is systems of linear equations. So let's get started here. All properties of vector addition and scalar multiplication hold also for matrices. And so this makes things pretty easy, right? All the definitions and all the processes we know for doing arithmetic and algebra on vectors, it's going to be the same rules for matrices. Under addition and scalar multiplication, we'll see matrix multiplication is quite a bit different. So some of the properties of matrix multiplication, the one that's very different from vector addition and scalar multiplication, right? Vector addition and scalar multiplication, we know that, so we're not even going to address that for matrices. We'll just say all those same rules hold for matrices. But for matrix multiplication, we do need to talk about the properties. What sort of manipulations are we allowed to make to these expressions? So the first property is that A times the quantity B times C equals the quantity A times B times C. So this is associativity of multiplication. It says it doesn't matter which pair you multiply first, so long as you don't change the order, the sequence of these matrices in a product. 2 and 3 here are both telling us we have a distributive property. Multiply a matrix across a sum of matrices. It's really distributed to each of them. But again, you do need to keep this A that was out to the left of the sum, the left of the individual pieces, because the order that you multiply matrices in does matter. Likewise, A plus B multiplied from the right by another matrix C does get that matrix distributed from the right to both of the pieces. So AC plus BC. But this is nice. We have a nice distributive property. We'll see later that a distributive property from both sides is all you really need to get the ability to sort of FOIL binomials of matrices. We'll do a little example playing with that. Property 4 says A times the identity equals the identity times A equals just A, right? This is saying that multiplication by the identity doesn't change anything. We said that's kind of like multiplication by 1 when working with numbers. Property 5 is saying that a scalar R times a matrix product, AB, really can be handled however you like. You can take the scalar to any piece of this that you want first and multiply in the rest later. You can multiply the matrices and then multiply the scalar outside, or you can multiply the scalar on one of the matrices and multiply the other matrix on the result, or you can multiply the scalar on the other matrix to start and multiply the remaining matrix on the result. Again, the important thing here is to keep the order that the matrices appear in the same. A always has to be to the left of B. You can put that scalar wherever you want. Property 6 is telling us something we really highlighted and noted in the last video, that AB does not equal BA in general. We saw an example where AB did equal BA, but we showed how that turned out in that example. And we mentioned, we showed how that turned out that way in that example, but we explained why it did, and that in general, that isn't true. We can't assume that will happen. This is telling us that multiplication of matrices is not commutative. Right? This is saying it's not doesn't have a commutative property. So we will always keep the order that we're multiplying matrices in very clear. We want to always make that very clear and keep it consistent. Now we saw linear combinations of vectors. Linear combination of matrices are just sums of scalar multiples of matrices. And we saw sums and scalar multiples of matrices work just as they do for vectors. So we define a linear combination of matrices just as we do for vectors. A linear combination of matrices A, B, and C can be expressed, like I said, just as with vectors, as a scalar A times matrix A plus a scalar B times matrix B plus a scalar C times matrix C, and on and on and on for however many matrices you have. If we write something like this for any scalars a, b, and c, that's a linear combination of matrices a, b, and c. Okay. So now some interesting results on multiplication. It turns out in any possible chain of matrix multiplication, we say in any possible chain because certainly the dimensions have to match up right so that the multiplication is even possible. You can easily write down matrix multiplications that aren't possible. So in any possible chain of matrix multiplication, the final product matrix that you have after multiplying a big chain of matrices together, that final product will have a number of rows equal to the number of rows in the first matrix in the product, the far left of your product, and the number of columns equal to the number of columns in the last matrix in the chain, the far right of the chain. So down below, you can see here, I've got that kind of diagrammed out in a example. If we multiply matrices A, B, and C in that order, A, then B, then C, from left to right, and that equals a matrix D, well, say we had these dimensions that I've written below. Say we had those dimensions on each of these matrices. A is 2 by 4, B is 4 by 1, C is 1 by 3, and D is 2 by 3. Well, just like we saw when multiplying any two matrices, that we need those inner dimensions to match, and the outer dimensions give us the size of the product matrix. We kind of think of the same way here. The inner dimensions of A and B must match. They're both 4 in this case. So you kind of think of them they're compatible and they kind of cancel out. And same with the B and C, their inner dimensions are both 1. So they match, that's good. We get both of those matches inside, that means this chain is possible. And what we want to see though is that the result of all 3 of those being multiplied together is a matrix that has the row dimension of the first matrix and the column dimension 3 of that last matrix. Right, so it works the same way as before. When multiplying two matrices, we thought of setting it up kind of like this and then kind of crossing out the ones that match and taking the outer dimensions as the size of your result. Same idea here, just more of them get crossed out. So that's how you can analyze a chain multiplication to make sure it really makes sense. Make sure all those inner pieces match up when you write out the sizes. So let's see some more facts here. Some things to caution about, some things about matrices that might not be intuitive based on our understanding of number arithmetic and number algebra on the real numbers. First fact, if you have the matrix equation A times B equals A times C and you know A isn't the zero matrix, it turns out you actually cannot conclude immediately that B equals C. Right, this is very obvious for solving equations in real numbers. This is a very standard property we usually use. Right, if I said that 2 times x equals if I say 2 times x equals 3 times 4, we'd usually think of this as being 2 numbers multiplied on the left, 2 and x, and 2 numbers being multiplied on the right, 3 and 4, where this number multiplied on the x is not 0. This is kind of like the a in this example. Well, then we can divide it off. And we'd say something like x equals 6. Right, but we used a necessary fact here was that dividing this guy off meant kind of dividing it off from the other side. And you have what's here must have been what remains here. 2 times 3. Right, so in general, we're just saying for numbers, yeah, it does hold that I can take an equation like this, and if A doesn't equal 0, I can kind of divide it off from both sides and see B equals C. That's not true for matrices, right? That same setup here, AB equals AC and A is not 0, does not imply that B equals C. So you can't think of matrices as these objects that you can just divide off so long as they're not 0. It turns out what we need is something more powerful called being non-singular. We'll talk about that much more coming up, but we want to be careful about some of these things we're used to doing with numbers that we can't now do with matrices. Very similar is that if you have a matrix product, AB equals the zero matrix, then it is not necessarily true that A and B were both zero matrices. Right? You cannot make that leap. With numbers, you can make that leap. With matrices, you can't. So for example, I've written down two matrices here, A and B. I wrote A is 1, 2, 2, 4. B is 2, negative 10, negative 1, 5. And you can check this. When you multiply A and B, you will get the zero matrix out. But neither A nor B was the zero matrix itself. So it shows that these little rules that work for numbers don't always work for matrices, specifically when it comes to matrix multiplication. Okay, so let's move on here. Very briefly, we want to mention that you can take powers of matrices. Since we just think of powers as being repetitive multiplication, and we know how to multiply, so long as the dimensions of matrix multiplication would make sense to do repetitive self-multiplication, right, raising to a power, we can do that. And it turns out in order for the dimensions to make sense, for the sizes of the matrices to make sense, it's required that A must be a square matrix, n by n, so that when we stack up a bunch of multiplications of A upon itself, all the inner dimensions match. N by n, n by n, n by n, and so on. If you don't have a square matrix, these multiplications won't be defined. So when we do something like this, take k copies of a matrix, a square matrix A, and multiply them all together, as you would expect, as is pretty intuitive, we will call that A to the k power. You can note that some basic rules of matrix, exponents still do hold for matrix powers. A to the r times A to the s is just A to the r plus s, right? Because this is just r copies of A laid out. This is s copies of A all laid out. Together, you have r plus s copies of A all laid out. Similarly, you can show that for integers r and s, A to the r raised to the s is A to the r times s, just like it is for numbers. A to the 0, we define that to be the identity matrix. Remember, when we are dealing with numbers, A to the 0 is 1. So it kind of makes sense, since I plays the role of multiplication by 1 for matrices, kind of makes sense that A to the 0 would be just the identity. We define it that way. In fact, when we do things like this, A to the 0 equals 1, we also just define that when we have a 0 exponent, it equals 1. It's not some intrinsic fact. We define it that way because it works out for useful purposes. So example 1 here, let's take a look at using some of these operations on matrices. Let's multiply and simplify the result. I've got matrices A and B written out in a big long expression here. Let's multiply them out and simplify the result. When I see 2a plus b squared, that's really telling me I have 2 copies of 2a plus b multiplied with each other. Then after that, I've got an a squared, just 2 copies of a multiplied together. I've got a b squared, same idea. I've got a 3b. And we saw we can actually distribute something like this through a sum or difference. So I can say this is a attached to the 3b, and 2 copies of b would make negative 3b squared. We saw I can also take this and take it in and multiply from the right on both of the pieces, distribute from the right. Notice I'm keeping these things very carefully in BA here and BA here. A was to the right of B, so it should be when I simplify as well, or when I multiply out. Same deal over here. Okay. All right, so from here, I don't have much to do, but I do need to handle this matrix product. Right, we said that we could distribute from the left or from the right. And what that really lets us do is perform what amounts to just a FOIL multiplication. Right? First, outer, basic multiplying binomials, inner, last. So do usual FOIL operation on this product of matrix binomials, and just make sure you keep everything in the same sequence. Every A that was to the left of a B should stay that way once you multiply things out. For example, first times first would give me 4AA, which is just 4A squared. Outer with outer would give me 2AB. A stays to the left of B. Inner times inner gives me 2BA. B stays to the left of A. I'm freely moving that scalar 2 around wherever I please, but the A and the B need to remain in a specific order. And finally, last with last gives me B squared. And now I can put like objects together. Right, I should specify this is equal to the previous line, this is equal to the previous line. Well, let me gather up my A squared terms. I've got 4 of them, 1 of them, plus 2 more. 4 plus 1 plus 2 is 7 copies of A squared. Let me gather up my AB terms. I've got 2 of them. That's a BA, that doesn't count here. I've got 2 copies of AB. And that's it, that's all. Now I can gather up my BA terms. I've got 2 of them here, 3 more here, and 1 more here. 2 plus 3 plus 1 makes 6 copies of BA. And finally, I'll gather up my B squared terms. I have 1 copy, minus 1 copy, minus 3 copies. I'm left with minus 3 copies of B squared. And that's it, that's fully simplified. Notice, since A and B do not in general commute under matrix multiplication, we cannot combine these two. These are not the same matrix. AB is not in general the same as BA. So we're stuck here. So that gives you a little kind of sense of what you have to be careful about when manipulating these matrix multiplication expressions. What I want is to think about just on your own, and maybe get in touch in office hours or by email to explore more about this. I want us to explore this idea. Can this result we ended up with, can this be factored into a product of matrix binomials? Scalar A times matrix A plus scalar B times matrix B, plus some other scalar C times A plus some other scalar D times matrix B. If I multiplied all that out, I would have an A squared term, I'd have a BA term, I'd have an AB term, and I'd have a B squared term. I've got all those here. So can I do that? Maybe something to consider. Maybe think about how you would approach that. If it was just an open-ended problem posed to you, how would you answer this question? How would you parse that out? Be sure if you do have questions about that, get in touch, but I want to leave that one open for you to explore a little bit. I don't want to wrap that one up nicely for you. I want to leave it open-ended. So now we're going to move on to really, I think, the most satisfying part of this section, and that is where we start taking systems of linear equations and writing them as matrix equations. Here we have all these operations we can do on matrices. Why do we care about doing those? Well, we care because we can write linear systems of equations as simple matrix equations. So let's see how this goes. Let's consider the most general linear system of M equations and N unknowns. If we're writing all this out very carefully, it's going to take this form where you've got M different equations. So the first one has first subscripts on the A values being 1 and B value subscript being 1. Next equation has the first subscripts on the A's being 2 and the subscript on B being 2. Right, so that first subscript here is labeling the equation number that we're in. You have the first one, second one, third one, all the way down to the M equation. And the second of those subscripts represents the column you're in, which really just represents the variable number, right? X1 is like the first column, X2 is like the second. So those little subscripts, the second indices, tell you which variable you're with. Everything with a second index of 2, every A value with a second index of 2 must be attached to an x2 somewhere. So we have 1, 2, 3, all the way out to n of those variables. Ooh, and I mislabeled this. This shouldn't be Bn, this should be Bm, because remember the subscripts on the B values tell you which row, which equation number you're in. We have M of those. So that should be the last one, has B subscript M. So this is just a general way to express any system of equations, an M equation, system of linear equations, and M equations with n unknowns. But what can we do from here? Let's think of what this really is. M different equations can really just be packed up into a single matrix equation where we put into the first component of the left side what we had in the left side of the first equation. So in the first component on the right side, we better put what we had on the right side of that equation, B1. And we fill up the second component of the left side with what we had on the left side of the second equation. We put in the second component of the right side what we had on the right side of the second equation, up here, B2. And we do that for all these equations and all these right-hand sides, all these B values, and build this little matrix equation this way. And as is, that's actually not so useful, but here's the really useful part. We're going to notice that from here, the left side of this equation, this big column matrix, right? This is just one big number here. It's the sum of all these values. So it's just one number here, one number in the second row, one number all the way down. So it's just a column. But that big column matrix there on the left side of that equation is really just A times X, where matrix A is this coefficient matrix, and matrix X is filled with, is a column of unknowns. Because think about how you would actually multiply A times X here to get the first entry of the result. You would take first row of A, first column of X, right? And kind of take a dot product, lay this guy over, multiply the corresponding pieces and add it up. So what would go here? A11X1 plus A12X2 and so on. Right? But that's exactly what we had at the previous step. The first entry had that whole left side of that first equation, which is what I'm developing here, just by doing matrix multiplication on A times X. So we see that we are going to express the original system that we started with, this guy, we have the coefficients all attached to all these unknowns, x1 through xn, and the right-hand sides, b1 through bm. We're going to express all of that just by going here and realizing the left-hand side is really A times matrix X, where matrix X is filled with the unknowns. We're going to write our original system as a simple matrix equation. A times X equals B, where B is this column of right-hand sides. We already know that equals A times X on the left. So we call it like this. We refer to it this way. So take that original system we started out with. If we can find the coefficient matrix and we make a X matrix, the column matrix of solution values we're trying to find, the unknown solutions we're trying to find, and B, let that be a column of the constant right-hand sides of the system of equations, then AX equals B represents the exact same information as the full system. Okay, so let's see an example. Say we have this system here, kind of a big thing to take in. Let's write this equivalently as a matrix equation, AX equals B. Let's identify what the AX and B would have to equal. So the A, remember, is just the coefficient matrix. Copy that down. Take the coefficients. Everything's in order, so I'm just copying them all down. There we go. And the X, that's just a column full of your unknowns, your X1, X2, X3, and in this case, we only have 4 of them. We stop at x4. And the b is the column of these right-hand sides, 1, 0, 2, 3. So instead of writing all this mess out, so long as we identify what a, x, and b equal, we can absorb all this information simply as a times x equals b. Much simpler. Right? 4 symbols versus how many symbols am I using here, right? A ton. It's a much more compact way to write the exact same system. Okay, let's see one huge value of doing this. One huge value of doing this is now there are some facts that we can very easily prove about these linear systems. Writing this matrix equation to contain all that same information is extremely convenient. Let's see why. So we can easily prove these facts A and B here. 1, the set of solutions of a homogeneous linear system forms a subspace. It's closed under addition, scalar multiplication, and it's non-empty. The set of solutions of a non-homogeneous linear system does not form a subspace. In fact, it's not closed under addition nor scalar multiplication, and it may not be empty. Oh, so it may be empty. There might not even be a vector in this set. That's just saying a non-homogeneous linear system might not have a solution. So let's prove this. I'm going to just prove fact A, and I will leave it to you to kind of follow what I did for A to try to prove B the same way. Let's prove A. Let's prove that the set of solutions of a homogeneous linear system form a subspace. Remember, when we say a homogeneous linear system, we mean that all the right-hand sides in this general system, all the right-hand sides would have to be 0 to make it homogeneous. Meaning in our matrix equation, the b's over here are all zeros. So this is like a 0 column matrix. And so our B here will just be a 0 matrix column. Well, that just means to prove this, we're going to try to show that the set of solutions of the homogeneous linear system forms a subspace. Remember what we have to show. It is closed under addition, scalar multiplication, and is non-empty, just like for vectors. So let's show how this works, right? These are just vectors. I'm referring to them as matrices often, but a column or a row can be thought of as a vector. And the column of unknowns, that's certainly something we can think of as a vector. So we have to check all these. And I'll show you how this is done so you can handle part B on your own. We start out by saying, let x1 and x2 be solution vectors to the system AX equals 0. Right? No matter what homogeneous system we have, we can take the coefficient matrix and write it here, take a column of the unknowns and write it as x, and set that equal to the 0 column with as many rows as A has, so that we are sure we are getting a homogeneous system. So then let x1 and x2 be any two solutions, anything you can plug in for this X matrix column and satisfy the equation. So in other words, assuming that x1 and x2 are solutions really just means we're assuming they solved this equation, right? When plugged into this equation, these equations are still true. So from there, we're trying to show if I've got these two in this space of solutions, I want to show that their sum is also a solution. This would be proving closure under addition. So let's see. Is the sum x1 plus x2 a solution to the original equation? Well, we can figure this out pretty easily. In order for this stuff to be a solution, plugging it in for x would have to leave a true equation. So let's plug it in. Let's see. When I plug it in, I get a times x1 plus x2. That's a sum of two things in the solution space. But what does this equal? We know we can distribute a matrix multiplication. So we can take this to be ax1 plus ax2. But what else do we know? We assumed each of these ax1 and ax2 equals 0. So this is zero matrix plus zero matrix, which equals the zero matrix column. So in other words, what we started with here does in fact equal 0, which means x1 plus x2 is a solution to the homogeneous system. Plugging it in for the x in this system, in this equation, gives you a true equation, right? We already showed it's true. So this gives us closure under addition. The set of solutions to the homogeneous system is closed under addition. Right. I suppose let's check scalar multiplication. Now I'll do this out to the right. I'm going to check scalar multiplication. The idea is now if x1 solves this equation, then does a scalar multiple also solve it? If so, we know the set of solutions to this homogeneous system is closed under scalar multiplication. So we test this. Again, I'm going to plug in for the x in this equation. I'll plug in c times x1. Where I'm not specifying what c is. C can be any scalar. That's important. It has to be left general. Right? So we're asking, does this satisfy the original equation? When we plug it in for x, do we get a true statement out? Well, a times this scalar multiple of x1 that we're plugging into the equation up here, we can take that scalar out front. Right? We saw in matrix multiplication, the scalars are free to move around wherever we please. And now we've already assumed that a times x1 is the zero matrix. So this is just the scalar times the zero matrix, which is zero matrix, right? Zero matrix times any scalar is still the zero matrix. That's a property we saw. So what do we have? We have that, yes, a times this scalar multiple of x1 does in fact equal the zero matrix. Implies c times x1 satisfies the system. It solves the system. I should say solves. So if x1 is a solution, any scalar multiple of it is 2. In other words, a set of solutions of the homogeneous system is closed under scalar multiplication. What to write here? Okay. So we have shown that it's closed under addition, closed under scalar multiplication. The last requirement is that it's non-empty, right? Meaning there has to always exist, no matter what homogeneous system I'm talking about. To say this set of solutions is going to be a subspace means, at very least, it can never be empty. There always has to be a solution to a homogeneous system. So is that true? Yes, it is. We saw that no matter what the homogeneous system, the solution where all the unknowns are equal to 0 does solve the system. So we always get the trivial solution, so it's non-empty. Since we know that trivial solution is always valid for a homogeneous system, that implies the set we're talking about is non-empty. There we go. We've checked all the boxes, right? We have shown closure under addition, closure under scalar multiplication, and that it's non-empty. Perfect. We've shown that the system, the set of solutions to the homogeneous linear system, forms a subspace. Okay. Well, like I said, I want to leave it to you to try to prove the second part. Just a sec here. Okay, what was I saying? Sorry, I had a technical difficulty. We're back. Yeah, I want to leave it to you to try to solve part B, which is pretty much the other side of it, right? We looked at proving that the set of solutions to a homogeneous system is a subspace. I want you to try to prove the same exact way I went through here, that this set of solutions to a non-homogeneous linear system does not form a subspace. And in fact, that it fails to be closed under addition, scalar multiplication, and is possibly empty, right? I want you to try that. The basic methods are all the same sort of things I did here, except in the non-homogeneous system, you don't have, clean up my mess here, you won't have 0 here. You'll have a non-zero column B, like the general systems we've been describing. Okay. So I want to let you try to prove that on your own. How about this? How about example 3 at the bottom of the page, where we're going to consider these two systems, where notice at the bottom of the page here, they're really the same system, just one's homogeneous and one's not. We have the same coefficient matrix in both cases. The left-hand sides of these equations are identical. So I think this is going to show us why we really care about the fact that homogeneous systems have solutions that form a subspace and non-homogeneous ones don't. How do we visualize this in a useful way? It's actually a pretty useful and important statement. Let's see how we can do this. Okay, so sorry for the abrupt change here. I cleaned up my screen here so that we got rid of all the previous mess we've been looking at. We've got our example that was at the bottom of our page that we're trying to look at. We have the same coefficient matrix in both systems. One's homogeneous and one's not. We want to see, what is that really doing visually? What is the difference between these? Why do we care that the solutions to the homogeneous version form a subspace, whereas these guys don't? Well, let's take a look. So we're going to solve this, kind of hide a lot of the steps actually. I just set up, since it's really the same coefficient matrix, I set that up in an augmented matrix. That's the way that we typically solve, is with an augmented matrix. And I put the non-homogeneous right-hand sides in a column. But since I also want to solve the homogeneous version, I also make a column of zeros to keep track of too. So it's like I'm solving the two systems simultaneously. What happens in this column will correspond to what was going on in the non-homogeneous system. What happens in this column, looking at this column as being augmented to the left stuff, this will tell us what's going on with the homogeneous system. So if I set this matrix up, I can just perform row operations on this as usual, try to take it to RREF to reduce row echelon form, and unpack to see my solutions. And we've done enough row operations that I'll leave that to you. You can check this with Octave or MATLAB, or do it yourself and check it. But when I do all this stuff under row reduction, I take it to my reduced row echelon form and I get this matrix. 1, 2, negative 1, 3, 0 in the top row and zeros elsewhere. Or you might see why that happened, because the bottom 2 rows are just a multiple of the first row. So you use that one to cancel all these out. Very quick and easy. Don't even need Octave or MATLAB, just a couple operations, 2 operations will take you. So this is our reduced row echelon form. We want to unpack this back into equations now. And remember to look at the, what have I got here? The non-homogeneous system. We should unpack it as if this column is gone, right? We're ignoring that. That just told us about the homogeneous system. To look at the non-homogeneous system, I just consider this is my augmented matrix and unpack it as usual. So my variables were x1, x2, and x3. So I get 1x1 plus 2x2 minus x3 equals 3. Now notice here, my system really reduced to just a single equation, meaning I have one lead variable and two free variables. Oops, free, not re. So the idea, as usual, to solve this system would be write x1, x2, and x3 in terms of parameters for the free variables. Then you can solve for the leading variable in terms of those parameters. So I'll let x2 be maybe r, and I'll let x3 be s. That means x1, solving this guy for x1, right, it'd be 3 minus 2x2 plus x3. But I know what x2 and x3 are, so I'll replace them up here. x2 is r, x3 is s. So there's our solution. We'll take it over here. So we can think of this as a vector, a solution vector. And we're saying all it really equals, the solutions to the system we started out with form a vector like this, x1, x2, and x3, where the x1 is 3 minus 2r plus s, the x2 is r, and the x3 is s. Okay, I want to do this in a very specific way though. I'm going to kind of decompose this into its constituent parts. I want to take all the stuff that has no parameters, r or s, put that in one vector, write it as being added to another vector that only has r parameters in it, and add that to another vector that has only s parameters. So in other words, I want to write this as 3, 0, 0 plus negative 2r, r0 plus s0, s. I just decompose this. You can check, add these back together, you'll get what we started with. This is perfectly legitimate. And now we can see what we really have is this fixed vector 3, 0, 0 plus r times a fixed vector negative 2, 1, 0 plus s times this last vector 1, 0, 1, 0. So let's keep our eye on that. For now, we're going to say this is like some fixed vector plus any linear combination of negative 2, 1, 0 and 1, 0, 1. So let's just keep our eye on that for now and go ahead and do the same process for the homogeneous system. So the homogeneous system would say, unpack your RREF form of your augmented matrix. But since we're only looking at the homogeneous system, this column, right, that came from the non-homogeneous right-hand sides, we're going to act like that was never there. We'll have 1x1 plus 2x2 minus x3 equals 0 now. And the other equations just give us 0 equals 0. Don't even have to write them. So let's do the same thing. Let's solve for x1, x2, and x3. I'll actually do it over here. Using x2 and x3 as free variables, r and s for those parameters. Then x1 is negative 2r plus s. Now, what can we do? I want to decompose our result here the exact same way. And when I do that, let's see what happens. Write this as a solution column, a solution vector. It's negative 2r plus s, r, and s. Now notice what we can do here. Make some space for myself. Same way as before, I'm decomposing this into the stuff that has an r and the stuff that has an s. And we should notice this looks exactly the same as what we got in the non-homogeneous system, except we don't at first have this fixed vector 3, 0, 0. All we have is r times negative 2, 1, 0 plus s times 1, 0, 0. So this is great. We're seeing that the homogeneous system is a set of solutions that's really just any linear combination of negative 2, 1, 0 and 1, 0, 1. The non-homogeneous system is that same thing, except it's all shifted or added by this vector 3, 0, 0, this fixed vector. But something about this stuff is what's important, right? That's what's kind of intrinsic to the coefficient matrix that define the systems. You get this sort of space of solutions defined by these guys, any linear combination of these two given vectors, negative 2, 1, 0, and 1, 0, 1. And when you add non-zero right-hand sides to your system, it just incorporates a little shift to those. Right? You're first adding some vector 3, 0, 0, and then taking any linear combination of those same vectors. So visually, what's happening here? This is what I want us to see. I've revealed how I think about this in a picture where the homogeneous system is just this, this linear combination of these two fixed vectors, plugging in, right, any value of R and S into this linear combination, adding the results back together will give you a solution to your homogeneous system. So in particular, plugging in R equals 0 and S equals 0 tells you the 0 vector is a solution, which is obvious, right? That's the trivial solution. We always know that's a solution to a homogeneous system. But we see that represented in this picture. I've got one solution, maybe, or one of these vectors, negative 2, 1, 0, written or drawn out here. I've got the other one, 1, 0, 1, drawn out here. And we're saying any linear combination. So take any amount of one of those guys plus any amount of the other and add them together. You'll still be somewhere in this plane that's swept out by those two original vectors, negative 2, 1, 0 and 1, 0, 1. So we're thinking that the solutions in this homogeneous system, in this particular case, form this plane, right? They're all just linear combinations of these guys, but linear combinations of two vectors will just sweep out a plane in 3D space. Any combination of these two will be still trapped in this plane. You can't really rise out of it. So that's what I'm thinking of. I'm thinking of this plane as forming the set of all solutions to our homogeneous system. And notice the plane contains the origin, which it should. The homogeneous system always has the 0 vector, the origin, as a solution. Now, when we took the non-homogeneous system, all we did was took that same linear combination of those same two vectors and first just added 3, 0, 0 to it. If you have studied vector addition very much and gone through this before, maybe it's clear that what we're doing is first displacing from the origin by this vector 3, 0, 0. I'll draw that in red here. I've got it written in black and white, but I want to make it clear. This is that shift. Let me just circle it in red here. That's that vector. It stretches out 3 units in the first variable's direction and nothing in the other variables. So I shift there, and then from that point, that's like my new origin, right? This guy moved to here. And that plane that I get of solutions is still just crafted out of linear combinations of these same two vectors as I had in the homogeneous system. They've just been shifted away from the origin. Yet still, that same plane shifted away from the origin is giving me my set of all my solutions. So that's how we want to think about this. That's why it's so important that a homogeneous system, for one, the solutions form a subspace. We saw subspaces are in R3 are really just lines and planes through the origin. That certainly matches what we're seeing here. The solution for this homogeneous system looks like a subspace. And when we take a non-homogeneous system, all we're doing is shifting that solution space off of the origin to some new point. Now, you might notice here that we had 3, 6, negative 9 as our non-homogeneous right side, but that vector 3, 6, negative 9 isn't where we shifted. So it's not just that whatever's here is the amount we shift by, it just causes some shift, in this case, a shift by the vector 3, 0, 0. How much you shift, or the vector that you're shifting by, automatically comes out of that general solution to your non-homogeneous system. So I hope this clears things up, right? This shifts that solution plane off of the origin, so it doesn't contain the origin, it can no longer be a subspace. Right away, that's an easy way to see why the facts that we proved earlier are true. I hope this kind of brings things together, right? Why do we talk about homogeneous systems? They kind of get at the guts of what this solution space looks like. Then if I want to look at a non-homogeneous system, I just shift by a vector, a particular solution, we call it, given by the constant part, the fixed part of that non-homogeneous solution. Not the stuff that it's a scalar multiple of a linear combination of two vectors, that other stuff that doesn't have a parameter. That's what you're shifting by. So I hope this kind of puts things into perspective. That's it for this video. Thanks for your attention, and I'll see you in the next one.